Hello and welcome to our archive lesson on concavity and the second derivative. So the first section, or the previous section that we talked about increasing and decreasing and how we use the first derivative to determine where a function was increasing and decreasing, and also to find relative extrema. So now we're going to take it one step further and use the second derivative to tell us about the concavity or the curvature of the graph, whether it's curved downward or curved upward. So the second derivative will give us that information. So the two things we're going to talk about is how we tell if a function is concave upward or downward using the second derivative, and then we're going to use that information to find what are called points of inflection. Now remember, when we used the first derivative, we found critical numbers and relative extrema. With the second derivative, we're going to find points of inflection. So points of inflection are sort of the cousin to the relative extrema. Right, we're going to find a change in the direction of concavity, and where we have that change in direction of concavity, we will have a point of inflection. Remember, where we had a change in direction of increasing to decreasing or vice versa, we had a relative extrema. Okay? Property of points of inflection, so just in the same way that we found critical numbers, and those were our candidates for relative extrema, we're going to do the same thing for points of inflection. We're going to have places where the second derivative is 0 or where the second derivative is undefined, and those will be our candidates for points of inflection, or inflection points. They're called either. Okay? So let's talk about the test for concavity. Very similar to the test for increasing and decreasing. You're going to first find all points of discontinuity. Then you're going to find the second derivative. Okay? So this time we're focusing on the second derivative. So I'm going to determine where the second derivative is 0 and where the second derivative is undefined. And as long as those aren't points of discontinuity, then those are going to be our candidates for our points of inflection. We're going to use those values to create our test intervals in our chart, just like we did with the first derivative, and then apply our definitions of concave up and concave down. Okay? All right, I'm going to talk about concavity and what it is and why we use the second derivative. Okay, so let me draw you two different curved graphs. Okay. In the graph on the left, we have negative and then less and less negative. As we go from left to right, we eventually get 0, and then they start increasing. And we start to get more and more positive. So the first derivative starts sharply negative, gets less and less negative, goes to 0, then becomes slightly positive, and then more and more positive. So the sign, or the first derivative, is increasing, right? It goes from negative and then to positive. F prime is increasing. Okay? The signs of the tangent lines, the slopes of the tangent lines, go from negative, and they get less and less negative, and then they go to positive and more positive. So they're increasing. Well, increasing means that its derivative is positive, right? Well, if f prime is increasing, its derivative is positive. The derivative of the first derivative is the second derivative. So that would indicate that their second derivative is positive, concave upward. Okay. On the other side here, they start out very positive, get less positive, shallower and shallower till we get to 0, and then they start out slightly negative and then get more and more negative as we go along. So this time, the slopes of the tangent lines, the first derivative, is decreasing. Right? They start out positive and then they go negative. They're decreasing. Their values are decreasing. So if something is decreasing, that means its derivative is negative. That means the first derivative is negative. Or the derivative of the first derivative is negative. That means the second derivative is less than 0, is negative. So that's how we're going to determine concave down. Okay. One way to remember this is by concave up is the second derivative. Two derivatives are positive. And concave down is the second derivative is negative. Okay, so you can remember that with the smiley face and the frown face to do our test for concavity. So let's go ahead and put this to work. Okay, our first one is we're going to call this function f, and it's going to be equal to negative x cubed plus 3x squared minus 2. And we're going to find the intervals on which the function is concave up or concave down. Okay, our strategy is number 1, points of discontinuity. This is a polynomial, so it is continuous everywhere, so it has no discontinuities. Step 2, find the second derivative. So we've got to go through the first derivative first. Minus 3x squared plus 6x. So second derivative, negative 6x plus 6. Step 3, find where this is 0, where it's undefined. See, negative 6x plus 6 is 0 when add 6x to both sides, when 6 is equal to 6x, or in other words, x is equal to 1. Negative 6x plus 6, it's a straight line. The graph would be a straight line. It's a polynomial, first degree polynomial. It means it's defined everywhere. It's continuous everywhere. Okay, so we only have just this one candidate for our points of inflection. Now remember, this is the same strategy that we used for finding relative extrema, or for finding where it's increasing, decreasing, but the difference is we're using the second derivative here, right? So I'm going to do the same things I did last, is I'm going to make a chart now. This time I'm analyzing, f double prime. I'm going to do the same thing though. Test value, fine. This time concave up or concave down, okay? So let's see, I have a break in the graph at 1. So negative infinity, or a break in the interval, not in the graph, I'm sorry, that's not accurate. Break in the interval here from negative infinity to 1 and 1 to infinity. All right, so test value. Pick 0 and 2. Remind ourselves where the second derivative is. Negative 6x plus 6. If I plug in 0, I get 0 plus 6. That sign is positive. If I plug in 2, I get negative 12 plus 6. That's negative 6. So that tells me I'm concave up in one interval, and I'm concave down in the other interval. Looks like that. Okay, so since we don't have a break in the graph there, I can sort of see that this graph would look something like this. Okay, again, a very rough sketch there. So this is concave upward, and we can abbreviate here, on negative infinity to 1, and we are concave downward on 1 to infinity. So that would be our final answer. Let's try another. This time we're asked to find our points of inflection. Remember, points of inflection are places where we change direction of our concavity. Remember, relative extrema is where we've changed direction in our graph, right? From increasing to decreasing, or decreasing to increasing. That was where we had relative extrema. Points of inflection, or inflection points, are places where we change curvature, where we're curved up or curved down. So we're going to do that same process that we just did. We're just going to add that one step in of analyzing, do we have a point of inflection or not? Okay. So our function here, f of x, is equal to x to the 4th minus 18x squared plus 5. All right, so first things first, points of discontinuity. This is a polynomial, so we have no points of discontinuity. Second, find the second derivative. So we have to go through the first derivative in order to get to the second derivative. So let me do that. 4x cubed minus 36x. Second derivative be 12x squared minus 36. All right. Third is find our candidates for points of inflection. That would be where the second derivative 0, second derivative is undefined. Okay, so that would be, let's see, 12x squared minus 36 equals 0. Factor out a 12. And that would mean when x squared is 3, that means when x is positive root 3 and negative root 3. 12x squared minus 36. Defined everywhere. It is a polynomial. It's a second-degree polynomial. So it has no breaks, no holes, no asymptotes. So we have our two candidates for points of inflection. And two places where we will break up our interval here. Let's do our chart. One, two. So again, F double prime, test value, sine, concave up, concave down. Okay. Our leftmost value is negative root 3. Negative infinity, negative root 3, negative root 3 to positive root 3, and then positive root 3 to infinity. And positive root 3 is somewhere between 1 and 2, correct? Because, let's see, square root of 1 is 1, square root of 4 is 2, and square root of 3 would be somewhere in between. Okay? And if you want to find out fairly close, root 3 is approximately 1.7, okay? All right, so test value, something between negative infinity and negative 1.7. Negative 2 would foot the bill. Something between negative root 3 and positive root 3, that would be 0. And something greater than 1.7 would be positive 2. Again, let's see, our second derivative is here at 12x squared minus 36. I'm going to test the sign at negative 2. So 12 times 2 squared. So 12 times 4 would be 48 minus 36. That would be positive. Plug in 0. 12 times 0 is 0 minus 36. That would be negative. 12 times 2 squared. So again, 12 times 4 would be 48 minus 36. That would be positive. And concave up, concave down, and concave up. So this has a bit of a look, something like so. Okay? All right, so do I have any points of inflection? Any places where I change concavity? And in fact, I do. I have, I'm going to call them POI, points of inflection, at x equal negative root 3 and x equals positive root 3. So they are, we're going to find the actual points. Negative root 3, comma, positive root 3, comma. So I'll have to do a little bit of work here. Negative root 3 to the 4th. Let's see, negative root 3 squared would be 3, and then another one of those would be another 3, so it would be 9. Or we could do answer raised to the 4th power minus 18 times answer squared, 5. Negative 40. And if you plug the other one in, square root of 3 to the 4th minus 18 times square root 3 squared plus 5, you notice that you get the same thing, negative 40. This is a symmetric function. In fact, it's an even function, so it's symmetric about the y-axis, but you can double check that. Okay. And so we have 2 points of inflection. So those would essentially be right there and right there. All right, that's it.